So welcome to the final video in the Collectorth Online series. In this video, we're going to put together everything we've learned in this course and create a image interpretation project from scratch. So in this video, I'm going to walk you through the image interpretation project planner, which is a document that we've put together here at Severe to help you plan out your image interpretation project. And then I'll walk you through this process together. So I have an example of this document, which is linked in this document itself. So we're going to walk through this together, how I planned out my image interpretation project and implemented it in Collectorth Online. So this planner, as well as the example that I filled out, will be available in the course materials. So the first step in planning out your image interpretation project, as we discussed earlier, is identifying some objectives. So my objective in this case is to quantify the land cover classes that are present in the country of Ghana for the year of 2022. And to accomplish that objective, my end product will be a wall-to-wall land cover map of Ghana for that year, 2022. And this end product will be generated using machine learning. So next, we want to develop our classification schema. In this case, I will use an existing one rather than creating my own. So the land cover classification schema shown here was developed by the European Space Agency for their world cover land cover map. And we can find this classification schema on their product user manual, so this is all open source knowledge. This is a global land cover map. So for your study area, you may choose to use a more local land cover map. But I chose this specific land cover map for a number of reasons, one of which is that it has a very broad classification schema, so it doesn't delve into the different kinds of forests or the different kinds of vegetation, aside from distinguishing between shrubs, grassland, and crops. So this very broad classification schema is going to be useful for this general land cover map that I plan to make. And the second reason I want to use the world cover land cover product is that it is publicly available in Google Earth Engine, which is going to be really useful when I try to implement my sampling design. So I just opened up Google Earth Engine here, and if we type in world cover, we can see that this is the land cover product that I'm after here, and it has some really great documentation about this product. And here you can see the classification schema as well as the color palette that they have here. So later I'll show you how I'm going to go about conducting a stratified sampling approach using the land cover classes identified in this map as my strata. But I also wanted to point out that this product user manual has the classification schema as well as the definitions for each class. And so I just borrowed those directly from this product. So here you can see this is the exact classification schema that I've copied over to my image interpretation project planner. So there's a lot of good land cover maps that are out there with good documentation like this, and you can use the same classification schema to directly compare your product against theirs. So now I have my classification schema, I can move on to identify what imagery I'm going to need in order to be able to distinguish between the classes that are in that classification schema. So first I want to think about the spatial resolution and range that we need to distinguish between those classes. So looking at my classification schema, distinguishing between classes like tree cover and shrubs, I'm going to need a sub-meter resolution imagery in order to be able to do that, right? Because trees and shrubs will look very similar at those medium and even high resolution images. Same thing for classes like herbaceous wetland and mangroves. Those are classes that are pretty similar, so that sub-meter resolution, something like a 30 centimeter resolution imagery would be very helpful to distinguish between those classes. As for the spatial range, I want to make a map for the entirety of the country of Ghana, so I will need imagery that covers the entire country. Now we can move to temporal resolution and range. So a temporal resolution of seasonal and ideally monthly is needed because we can see that, for example, for classes like permanent water bodies, we have to identify that what we think is permanent water is in fact water for more than 9 months out of the year. And this seasonal or monthly temporal resolution will also be really helpful in identifying cropland and distinguishing cropland from other vegetation land cover classes, because it will allow us to identify a sowing or planting date as well as a harvest date. So now that and then for temporal range, we need a temporal range of January 2022 to December 2022, because we're trying to make a land cover map that captures the year of 2022 as a whole, so we want images for that entire range. So now we need to answer this question: are the default imagery sources in Collectorthon necessary to accomplish our objectives and our spatial resolution and temporal resolution and range that we noted above? And if not, we'll have to import external imagery into our Collectorthon institution. So for my purposes, the default imagery sources in Collectorthon are sufficient to accomplish these objectives, right? Because Mapbox and Google Earth Pro will provide the sub-meter spatial resolution for most locations, and Planet NICFI imagery will provide that that high temporal resolution, because my time period of interest is in 2022, and Planet NICFI offers monthly mosaics for any time past August of 2020. So I'll be able to use the Mapbox and Google Earth Pro for that high spatial resolution, and I have that Planet NICFI imagery for the high temporal resolution. Now, obviously, this is not ideal, right? In a perfect world, we would have a single set of imagery where we know that it was acquired in sometime in 2022, and it's very high spatial resolution. But we're working with the limitations of open source imagery for this project, and I can be more careful in my response design to note that I will only use samples where I have very, very high resolution Mapbox imagery, and I have a lot of good cloud-free observations in the planet imagery. But even though this default data will be sufficient for my image interpretation project, I'm planning to use a machine learning classifier in order to make my end product. And because of that, I want to provide all of the data that I plan to use for that machine learning classifier to the data collector, which is myself. So I'm also going to import Sentinel-1 and Sentinel-2 false color imagery, as well as the Shuttle Radar Topography Mission digital elevation model. I want to add all of that imagery to my Collectorthon project because I plan to use all of that imagery when I train my classifier and make my end product. So now I can move on to my sampling design. So the first step is to figure out if I want to use clusters or not. Since I won't be buying any imagery and I won't be going out into the field to collect ground truth data, I won't use a clustered sampling approach. But in this case, I will use land cover class as a strata. So I'll use that world cover product I talked about earlier to stratify my region of interest based on the land cover class. And so this will really help to provide my machine learning classifier with examples of rarer land cover classes like mangrove forests. And then within each of those strata, within each of those land cover classes, I will use random allocation. So I'll randomly distribute an even number of points within each land cover class. And finally, I have to decide what my sample size will be. So in this case, again, since I'm using a machine learning classifier, I'll use that equation where n equals 10 PC, where n is the number of sample points that I plan to collect, p is the number of spectral bands I plan to use in my classifier, and c is the number of classes in my classification schema here. So here you can see all of the spectral bands that I plan to use in my classifier. So there's 16 bands total, and so that will be our p will be equal to 16, and c will be equal to 11 because in the classification schema noted here, there are 11 classes. So that gives me a total sample size of 1,760 points. But we are going to recommend that when you're conducting your image interpretation project, you limit your number of points to at most 250 points, and this is just for time purposes. So you can make a note of what your ideal sample size would be but when you go ahead and implement this project in Collectorth Online, use no more than 250 points for your sample size. So now we want to make a note that if you plan to use clusters or strata, your sampling design will be a little bit more complex to implement in Collectorth Online. So if you don't have a lot of experience with Google Earth Engine or another method to implement a stratified sampling design or a clustered sampling design, we will recommend that you go ahead and use neither clusters nor strata, because it will make creating your project in Collectorth Online much easier. Excuse me. But if you do plan to use clusters or strata, you want to list out the steps that you're going to take in order to get a spreadsheet of points that you can then upload into Collectorth Online. So here I've noted what those steps are, and I'm going to walk through this process for us a little bit later in this video. Finally, we want to conceptualize our response design. So first, are we going to use an aerial-based assessment unit or a pixel-based assessment unit? For me, I'll use an aerial-based assessment unit because a lot of the classes in my classification schema require an aerial-based unit. So we'll see that for the land cover class of tree cover, the description says right here that the class includes any geographic area dominated by trees with a cover of 10% or more. So that requires an aerial assessment unit. So if you are going to use an aerial assessment unit, you have to determine what size you want to use. For me, that size will be 60 meters by 60 meters, and this will match the coarsest resolution of my input data to my machine learning classifier, which is bands 9 and 10 in Sentinel-2 data. And if your assessment unit is aerial, you also want to come up with a good rule for yourself to follow when you're collecting this data about what you're going to do for assessment units that are mixed in terms of the land cover class that show there. So the rule that I've created for myself here is that assessment units that are 90% or more of one land cover class will be classified as that class, and assessment units with less than 90% of one land cover class, so there's mixed land cover classes within the assessment unit, I'm going to flag those and remove them from the data collection process entirely. And then finally, we want to come up with our questions and responses for our CEO project. So I'm just making a static land cover map for a single year, so I'll just have one question, which is what is the land cover type in 2022, and my responses will be the land cover classes that are in my classification schema. So I've filled out the image interpretation project planner. Now I'm going to follow these steps below to implement this project design in Collectorth Online. So the first step in the instructions here is to look at our answer to question 4C in this document, where we recall if we want to import external imagery into our institution. So if we do need to import external imagery, we will go ahead and do that now, and if not, we can skip ahead to step B. But since I want to import imagery into my project, I'll show you how to do that right now. So let's navigate to Collectorth Online just by opening our browser window and typing it into our search engine, clicking on the first result, and then clicking Open CEO here. Of course, we want to log into our account, and then we want to navigate to our personal institution here on the left by clicking Visit. So we're going to click the Imagery button and then click Add New Imagery. So I'm going to breeze through this pretty quick because we covered it in Unit 2, so feel free to go back to that video if you can't recall how to import a certain type of imagery. So I want to import Sentinel-1, Sentinel-2, and the Shuttle Radar Topography mission data, which is a digital elevation model. So let's start with Sentinel-1. So we can give it a title and say Sentinel-1 Ghana. We'll make our default year 2022, our default month January, and we will use that default band combination there where VH is assigned to red, VV to green, and the ratio of the two to blue. We'll set our minimum value, which 0 is a good one for Sentinel-1, and a good max value for Sentinel-1 is 0.3. And we'll add that imagery to our institution. We can see it popped up there, so we can move on to Sentinel-2. And again, I'll make the default year 2022 and the default month January. For my purposes, I want to use a true color image, but we can also use those false color images as well. And just like Sentinel-1, 0 to 0.3 are some good visualization parameters. And finally, I'll specify a cloud score of 10. Alright, so we've added both Sentinel-1 and Sentinel-2 to our image, or to our institution rather. So now we want to import our SRTM data into our institution. And so we need to use the Google Earth Engine image asset option in order to do that. So if you can recall from Unit 2, we need a asset ID as well as some visualization parameters. So let's navigate to Google Earth Engine in order to figure out some good visualization parameters. So I already had a Google Earth Engine tab open. So I'll go ahead and search for the Shuttle Radar Topography Mission data, which is listed as SRTM. You can see it's right there. And we will go ahead and import that into our script here. It's just hiding behind my picture down there. So I'll click Import. And so then what we want to do is navigate to the country of Ghana and just make a very basic geometry around the country to clip the SRTM image to that. And this will help us to get some good visualization parameters. So I'll just rename this to Ghana. And I'll make a variable called SRTM clip. First, I'll rename the import as SRTM. And I will use the clip method in Google Earth Engine to clip the SRTM image, which will cover the whole globe just to the country of Ghana. I'll also make a variable called bands, which will tell me what the band names are for this SRTM clip image, and I can get that information by using the band names method. So I'll print that to the console over here on the right, and I'll also define a variable called visualization parameters, or VP, which I'll just leave as empty curly braces for now, but we'll actually fill that in later. And then we can just go ahead and add our SRTM data to the map. So we'll use those empty visualization parameters right now, but Google Earth Engine will actually already be able to add it to our map, and we'll just give it a name here as well. So we can go ahead and click Run. We can see that our SRTM data consists of one band called elevation. And then we also want to find out our good visualization parameters. So what's a good minimum and maximum value for this data set? So right now it's just showing up as all gray because there's not a lot of topography in the country of Ghana on a scale of kilometers like other countries. So we will go ahead and use the stretching parameters by clicking on this gear icon here under layers. So I'll go to custom and go to 100% stretch to get the minimum and maximum elevation in Ghana. So we can see there's a minimum elevation of 0 and a maximum elevation of about 675. So now I know our band name is called elevation. That's the only band in this image, and I know a good minimum and a good maximum value as well. So then I'll go into my visualization parameters here, and I will say bands is elevation. I'll say our minimum is 0, and I will say our maximum is 675. So this is going to be our asset ID here. So we will copy that and bring it over into Google Earth Engine. And we will get rid of the quotes. And then we can just use our visualization parameters that we just made and copy those into Collector Thumbline. We might want to run the script one more time just to make sure that everything's working well. before we bring it into Collector's Online. And yep, it looks good, so we can copy those visualization parameters in here. And then finally, we'll just give it a title and say SRTM Ghana. Then we'll click Add New Imagery. So now we've got our 3 imagery sources available here, so we are ready to move to the next step. So let's go back to the Image Interpretation Project Planner and see what we should do next. So now it asks us to look at our answers to question 5A and 5B when we were creating our sampling design. And it says if you answered no to both 5A and 5B, proceed to step 3, or step C rather. But if we did answer yes to 5A or 5B, we'll need to create a spreadsheet file for our sampling design that looks similar to what's shown below here. So going back to question 5A and 5B, those are asking if we wanted to use clusters or strata. Since I do plan to use strata, I will have to make a spreadsheet of my sampling points to implement this sampling design in CEO. So I'll show you how to do that right now. So we can use a number of different tools in order to accomplish this. We just want an output file that's a CSV or comma separated value file, which you may think of just as an Excel spreadsheet that has the following columns. So we want a column that says plot ID that just consists of integers. We want a column for longitude, which will specify the longitude of each of our points. And we want a column called lat, which will specify the latitude of each of our points rather. So this is what we're after, right? Something like this. So how would I go about implementing a stratified random sample like the one I came up with and getting a spreadsheet like this? Well, I'll show you one way to do it in Google Earth Engine, but this is certainly not the only way that you can conduct a stratified random sample. So I'll go back to our Google Earth Engine script here and delete everything that I put in to get those visualization parameters for Ghana. And I'll show you how to conduct a random stratified sample. So our first step for conducting a random stratified sample is going to be finding our strata, right? So earlier I said that I was going to use this world cover product to conduct my stratified sample. So I'll go ahead and import that into the script now. And I will call it world cover. So if we just start off by printing this to the console, we'll see that it's an image collection consisting of one image, which is the land cover map for 2021. So in order to extract that image out of the image collection, I need to first convert this image collection to a list, and we can do that using the toList function. And then I can use the .get function to index the list and get the first item in that list, which will be at the 0th index, because in computer science we start counting at 0. So when I run that, first we have to specify a length of our list in the toList function. So I will write a 1 there to specify that we only need that list to be of length 1. And of course, we can always reference our Google Earth Engine documents to see what sort of arguments I need to feed to the toList method. So we are trying to run toList on an image collection, so I can just click on this to see what type of arguments we need to feed to this method. So again, the toList method converts this image collection to a list. The .get method will get a certain index from that list, in this case the very first index. So we can just go ahead and print the world cover toList to our console to see what that looks like if we're not familiar with how to convert an image collection to an image. And we can see that it is in fact an Earth Engine image. So now we can go ahead and clip that image to Ghana. But first we need to specify our region of interest itself. So earlier we used a general region of interest, just a polygon around Ghana. But for our stratified sample, we can get a little bit more specific with our boundaries. And we can do that by using an open source feature collection data set within Google Earth Engine. So the one that I like to use is the United Nations Food and Agriculture Organization's GAUL dataset. This stands for Global Administrative Unit Layers, and it just has all of the country boundaries in the world. So we can see, if we click on Table Schema here, that this feature collection dataset has these different columns here, and the descriptions of each of them here. So we can see that this code for ADM0_name stands for the country name. So we can use that information to filter our this data set to the country of Ghana specifically. So I forgot to import the GAUL data set into my script, so I'll click import and rename it GAUL. And then I will use the EE-filter function to filter that GAUL data set, which contains all of the countries in the world, to just Ghana. So I can do that like so. And I have to use the .filter method and then say EE-filter equals. And here's where I want to say that column name that we copied earlier from the GAUL schema, ADM0name, which just means the country's name, and then separate that with a comma from the country's name. And we have to spell it correctly and use a capital letter. So I'll run that just to make sure that it's working well. And then I'll try to clip this image to the country of Ghana. So let's see if that worked. So I'll say Ghana world cover equals world cover to list dot clip. So this clip method will just clip the image over the entire world to Ghana, and let's run that. And we'll see that that's not going to work because this is still a list. We indexed the list and got the first element, but we still need to turn this list back into an Earth Engine image. So I can say EE image, world cover to list, and then clip it to our region of interest. And now that worked, we can go ahead and add it to the map. So this is the world cover map for Ghana. We can see it already included a nice color palette for there for us. And to know what each of those different colors means, you can just search up that world cover data set in Google Earth Engine right here. So this gives us a nice idea of what the land cover trends might be like in Ghana. And now we can use this data set to conduct our stratified sample. So let's make a variable called strat sample, and we will use the stratified sample method in Google Earth Engine to do this. So first we want to give it the image that we want to use, which is our world cover map clip to Ghana. Say .stratified sample, and then we have a couple of parameters we want to give. So the first is the number of points. If you'll recall, we found out from my sample size that I wanted to get 1,760 points total. We have 11 land cover classes present here, so I'll divide that to get 160 points per class. The next thing I want to do is get the region. So our region in this case, of course, is Ghana. And then I also want to get a scale. So the scale of this world cover map is 10 meters by 10 meters. So I'll just use that scale. And then finally, I want to include this geometries argument. And this is really important when we're doing our stratified sample, because if this is set to false, which is the default, it won't include the latitude and longitude of our points, which of course is going to be crucial when we want to upload this to Collect Earth Online. So before I run it, let's add that stratified sample to the map so we can get an idea of how our points are distributed in the area. And that is going to take a second to load. So while we are waiting for that, we can go ahead and start with our final step, which is exporting the sample to our drive. So again, we can search that up in the docs here if we're not familiar. Export graph.table. See to drive. So we want to feed it a collection, and then we also want to feed it a file format as well. So we'll say our collection is going to be that strat sample variable, and then we will give it a description as well. So we can just say Ghana strat sample v3, and we can give it a file format. So at the end of this stratified sample, we want a CSV. But in this case, the way that Google Earth Engine exports a CSV is not going to be ideal for us to feed that into Collect Earth Online. So I'll actually show you how to export it as a GeoJSON file, and then we'll convert that to a CSV later on. So we can go ahead and run this. As we can see, our stratified sample is taking a while to add to the map because it's over 1,500 points. So let's run the script again, and we can start this export process too. So we can see once we ran that script, I clicked over very fast, but this tasks button lit up over here. So if we click that, we can see there's a task ready for us to run here. So this will be our export to Google Drive, and then we can go ahead and click run. So now that that is running, it will take about a minute to get into our Google Drive, and then we can download that file from our Google Drive and convert it from a GeoJSON to a CSV. So in order to do that, I'm going to show you how to do it using a free website, but you can also do this in a Python notebook if you wanted to, or use some other software to do so. This, of course, is not the only way to do this. So I just searched GeoJSON to CSV, and this is the website that I'm using, https www.convertcsv.com. So I'm going to have to download the GeoJSON from my Google Drive first, so we need to wait for this to finish before we do this. But it's very simple. All we have to do is choose a file here and then click Convert GeoJSON to CSV. Going back to our script here, we can see that our stratified sample layer has loaded in. So these are all of our points here. And we can see that even for these rarer land cover classes, like mangroves, which are specified by this light green color down here, we have a high density of points because we have an equal number of points for these rarer land cover classes, as well as for these more prominent land cover classes like forest cover. So those are all of our sample points. And so this is going to allow us to get a really good balance of land cover classes so that we can get a balanced data collection set and train our classifier on all these different land cover classes. So our task has completed. We can click Open in Drive to see where it got exported to. So this is our file here. So I will go ahead and download this to my computer by right-clicking and clicking Download. We can see it got downloaded here. So I will go back to this website and click Choose File and then upload my GeoJSON here. And then all we have to do is click Convert GeoJSON to CSV. If you want to know what's going on behind the scenes here, instead of just blindly trusting this website to convert it correctly for you, we can just click on our download and drag it into a browser, and this will show us what the GeoJSON actually looks like. So we can see it's what you may know as a dictionary if you have a background in programming, but it's basically just a list of this data. So here you can see that for each feature in this feature collection, we have a list of coordinates. So these are the coordinates that we're actually after. So this is the longitude and this is the latitude, and so these are the this is the actual information that we want to extract out of this data set, right? This is all that we're after, is the latitude and longitude of each of our sampling points. So going back to our website, we can see that after we clicked convert GeoJSON to CSV, it's saved our result for us, and we can go ahead and click download result. Oh, I did not actually upload my data set. So after I clicked convert GeoJSON to CSV, we can see it now understands that we want a latitude and a longitude for each of those points. So that's looking good. We can go ahead and click download results. So going to our downloads folder, I'm just going to drag this to a folder I made called CEO demo. And then we can open this file in Excel and take a look at it. So earlier I mentioned that we want to give our columns specific names when we upload this data into Collectors Online. So instead of latitude, we want it to be in all caps LAT, and instead of longitude, we want it in all caps to be LON. We can get rid of these other columns by clicking delete for the entire column. And then lastly, we need a column called plot ID, again in all caps, and we just want this to be integers. So we can type in a 1 there and then use some Excel math. Oops. In order to get a number of, or rather a column full of integers. And then we can click at the bottom right and drag all the way down. So now that we have a CSV file with a column for lat, lon, and plot ID, we are ready to proceed. We are ready to go ahead and upload this sampling design into Google Earth Engine. So finally, we want to make sure that it's saved as a CSV, and we're going to note that it's ready for upload. So I'm just going to call it upload Ghana strat sample, and I'll save it in that same folder that I'll return to later. So that is how to conduct a stratified sample using Google Earth Engine. So now I'll go back to our project planner and see what we should do next. So we've imported our imagery, we've conducted our sampling design. Now we just need to create our project in Collectors Online and implement the sampling design and response design that we noted here. So we can go ahead and do that right now. So let's go ahead and open Collectors Online and create this project and bring it to life. So again, we can just navigate to our homepage, and let's navigate to our institution on the left by clicking that visit button. And then we'll click create new project. So again, just like with importing imagery, we already covered this back in unit 3, so I'm going to go through it pretty fast, but just refer back to that unit's videos if you are confused about any of these steps. So I will call our project Ghana land cover and give it a description. And click next. We'll have our base map be that map box data. We want to include Planet NICFI public, and then we want to include Sentinel-1 and 2, as well as that SRTM data that we imported earlier in this video. Then for plot design, we are going to click CSV file and upload that file we just created. So again, let's navigate to that folder we were just in and click this file that we made. And then we'll specify if we want a circle or a square plot. I want a square one, and I want the plot width to be 60 meters. And again, this is what I noted in my project planner up here. So you'll just refer to your project planner as you go through the project creation wizard in Collectors Online. Then we want to implement our response design. So we have a aerial sampling unit already. And I will just go ahead and use this center for the sample, so it will just be one sample per plot, and then we can implement our response design where we're only taking assessment units that have 90% or more one land cover class. And I recommend using this center option when it comes to sample generation because it will make the data post-processing after you're done collecting your data much easier. Then we'll click next. And now we want to implement our question and responses we noted in question 6D on our project planner. So my question I wanted to ask was, what is the land cover type in 2022? And I recommend simplifying this question because, again, it will make your post-processing much easier. So I know that I want to ask what's the land cover type in 2022, but I might just simplify it to land cover 2022. And also make sure you don't put any commas in here because that might alter your data post-processing because comma-separated value files use commas to identify where different columns are. So I'll go ahead and add that survey question, and then I'll add each response. Again, I will use underscores rather than spaces, and that will just make my life much easier when I go to post-process this data and turn it into my final project. So we want a land cover class for tree cover. We want one for shrubland. We want one for grassland. We want a cropland layer built up, as well as bare or sparse vegetation. I'll just say bare. We also want permanent water. And we also want snow and ice, as well as moss and lichen. We want herbaceous wetland as well, and we want mangrove forests. That should be all of them. 1, 2, 3, 4, 5, 6. Yep, we've got 11 here, and then of course we remember we can change the color that we want each response to appear as here. So I'll just do that very quickly. And again, we have to click the save icon to make sure that our question and our responses are saved. So after this, we can just go ahead and click Create Project, and we will go ahead and start collecting our data for each of our points. And again, we're going to want to use those image interpretation practices when we interpret each point. So I've got all my responses listed there, as well as my question. I can go ahead and click Next. You can also create rules for your project, but I'm going to skip that step. Click I agree to the terms of service, and then create my project. So now we can see our project has been implemented successfully. There are our sample points. We have all of our imagery added, and we are ready to go ahead and collect our data. So let's go ahead and do that. So I'll click Collect here on the right. And go to Unanalyzed Plots and start collecting my data. So now it's just a matter of collecting data. So this is a somewhat tedious process, but I will see you at the end when I am done collecting my data, and I'll show you how to download it from Collectors Online and translate it into my end product, which will be a land cover map. Collectors Online has received financial support from NASA, the U.S. Agency for International Development, or USAID, the Food and Agriculture Organization of the United Nations, or FAO, the U.S. Forest Service, Silvacarbon, Google, and the Spatial Informatics Group. It was co-developed as an online tool housed within the Open Forest Initiative of FAO. Collectors Online was initially developed by Servier and is now supported by a broad base of partners. And it was inspired by Collect Earth, a desktop software developed by FAO. The development team of CEO includes Arthur Lewes, Jordan Combs, Matt Spencer, Richard Shepard, Oliver Baldwin Edwards, Sif Beery, Roberto Fontanarosa, Francisco Delgado, Githika Tondapu, Billy Ashmal, Nishanta Kanal, John Dilger, Karen Dyson, Karis Tennyson, Kel Markert, Africa Flores, Emil Sherrington, and Eric Anderson. The Collectorthon curriculum was organized by Sevier's Science Coordination Office, with individual models created by NASA, USAID, NASA's Earth Observatory, the Spatial Informatics Group, and Sevier's Science Coordination Office. These individual modules were created by Crystal Wespestad of Spatial Informatics Group, Holly Rybeek and Robert Simon of NASA Earth Observatory, Billy Ashmall, and myself, Mickey Maganini, of Sevier's Science Coordination Office. Review of the material was conducted by Sevier's Science Coordination Office, including Kelsey Herndon, Emil Sherrington, Billy Ashmall, Deanna West, Katie Walker, Lauren Carey, Jacob Abramowitz, Jake Ramthen, Natalia Bermudez, Stephanie Melik, Emily Adams, Stephanie Jimenez, Vanessa Martin, Alex Goberna, Francisca Delgado, Biplav Bhandari, and Amanda Markert. Crucial insight regarding the development of the curriculum materials was provided by Claudia Paris and Andrea Puzzi-Nicolau. Review of the material was also conducted by Bart Kroll and Laura Cray of ITC, the Faculty of Geo-information Science and Earth Observation at the University of Twente. The course and unit banner images used in the course were created by Gianluca Ambrosi of ITC.